Hi, everyone. Welcome back to MATA02, the Magic of Numbers. Today, we're going to be going back and reviewing Fermat's last theorem, but spending a little bit more time to really try to understand what's going on there, and also walking through the proof of it a little bit more carefully, since, as you all know, you all do have a proof question on the quiz, and there will be one on the final, so I'm trying to and a lot of people seem a bit more confused about that. So we're going to walk through a bit more slowly, as well as review some of the other applications of Fermat's last theorem that we have been covering, such as in computing powers or in computing roots, which we covered last Wednesday. So let's go ahead and get started by, reminding ourselves not last theorem. It's not what I said, Fermat's little theorem. Fermat's last theorem is something completely different. So Fermat's little theorem. So let's review what it states. Well, the statement is, if you let P be a prime number, so this is a condition. So this is something you need to be true for the theorem to matter at all. And if A is not congruent to 0 mod P, then we know that A to the P minus 1 is congruent to 1 mod P. You can also rephrase it slightly differently. If for any A, including 0, A to the P is congruent to A mod P. But that's just a special case because 0 to any power is always equal to 0. So you can't get 0 to some power is equal to 1. Okay. So what are the two applications that we discussed? Well, we had two major applications. We had finding large powers, and we had finding certain roots in modular arithmetic. So what do those look like? Well, if you have A to the 1002, well, mod, say, 11, well, that's congruent to A squared mod 11. And that's just because we have Fermat's little theorem, and A to the 10th is congruent to 1. And if A to the 10th is congruent to 1, then A to the 10 times any integer is also congruent to 1. And so you can just cancel all those out. Similarly, the cube root of A mod 11 is congruent to the cube root of A to the 11 because of Fermat's little theorem again. So you can multiply by A to the 10, which is congruent to the cube root of A to the 21. But you know that 21 is divisible by 3, so this is congruent to A to the 7 mod 11. So under certain conditions, you can turn a problem of finding a root into a problem of finding a power, which is nice because we know how to find powers. Okay, so hopefully that's all review. You will need to know that for the quiz tomorrow. Oh, come on. So let's review these algorithms. So when I was giving you these algorithms originally, I didn't really write them as a step-by-step cookbook because I wanted us to try to figure out what was going on. But here, let's write out each of the steps that we need to do to actually solve these kinds of problems. So for a large power, well, let's think about what the conditions are. The conditions are that P has to be prime and A has to be not congruent to 0 mod P. Of course, if A is congruent to 0 mod P, then it's really easy to take a power because it's just 0. But these are the conditions we need to start off using this sort of algorithm, using Fermat's little theorem. So the first thing you do is you divide M by, wait, do I have a D there? That should be a P. So P minus 1. So division by a remainder with remainder. Then if you do that, then A to the M is congruent to A to the R mod P. Okay, so let's see an example of this. We saw one a moment ago, but let's see a slightly less trivial example. So 2 to the 125 mod 13. Well, what's that equal to? Well, P minus 1 is 12. And so you take 125, divide that by 12. Well, that's 1, that's 0, 5, 0, remainder 5. Okay, and so that's remainder 5. That means that this is congruent to 2 to the 5 mod 13. And now at this point, there are a couple things you could do. One thing you could do is, of course, if the power is small enough, you can brute force it. So I happen to know that 2 to the 5 is 32. And if you have a calculator, you could also figure out that 2 to the 5 is 32, which means that you can just take that, divide it by 13, find the remainder, and that gives you the answer. But if the power is too big, then you might want to break it up into powers of 2. So this is also congruent to 2 to the 4 times 2 to the 1 mod 13. And of course, 2 to the 1 is congruent to 2, 2 squared is congruent to 4, and 2 to the 4th is congruent to 16, which is congruent to 3 mod 13. And so overall, this is congruent to 3 times 2 mod 13, which is just 6 mod 13, right? And of course, if you had done it the other way, we would have found it as well. So that's also congruent to 32 mod 13, which if you subtract 26, if you divide by 13, the remainder is going to be 6. And so you get the same thing either way. Okay, so that's finding large powers. That's relatively straightforward. It turns it into a division problem if P is prime and A is not congruent to 0. Okay, and what about finding certain roots? So this is a little bit more complicated because it doesn't always work. But we still have some intuition, right? So our intuition is that kth roots are easy if you can write something as a to the km, because the kth root of a to the km is just a to the m by using the rules of power of exponents that we discussed in the second week of class. And then the other intuition is that for any a, you can rewrite a as a to the 1, right? So clearly a is a to the 1. And that's congruent to a to the p minus 1 times l plus 1 for any integer l. Again, by Fermat's little theorem. So you can add any multiple of p minus 1 to the exponent, and you're going to get the same thing. So if we use this intuition, one way to solve this, which won't always work but one way that you can try is, let's say we're going to take the 5th root of 10 mod 17. Well, then we know that 10 to the 16 is congruent to 1 mod 17, right? Because any a to the 16 is congruent to 1 mod 17. So moving on, we know that, well, you could try writing out each of the different equivalent powers. So 10 to the 1 is congruent to 10 to the 17, because 1 plus 16 is 17, is congruent to 10 to the 33, because 17 plus 16 is 33, which is congruent to 10 to the 49, which is congruent to 10 to the 65. And you'll notice that 65 is a multiple of 5, so we can stop there. Plus, we know that the 5th root of 10 is congruent to the 5th root of 10 to the 65. But of course, that's just congruent to 10 to the 65 divided by 5, which is congruent to 10 to the 13 mod 17. And there are a couple of things you could do here. One of them is you could be like, well, you can just compute out, so that's what, 10 trillion, divide that by 17, find the remainder. But of course, we're going to use a slightly different strategy, which uses breaking this up into powers of 2. This is congruent to 10 to the 8 times 10 to the 4 times 10 to the 1, because 8 plus 4 plus 1 is equal to 13. And well, let's solve this. So 10 to the 1 is congruent to 10. 10 squared is congruent to 100, which is congruent to 15 when you get the remainder when you divide by 17. 17 times 5 is 85. Which is, and so 10 to the 4th is then congruent to 225. And this turns out to be congruent to 4. So you'll want to divide by 17, get the remainder, and so on. And then 10 to the 8th is congruent to 16. Now, 16, you might notice, is 1 less than 17. And so sometimes when you have numbers that are very close to your modulus, it's easier to rewrite it in negative form. And so this happens to be congruent to -1. And you plug these things back in, and you get this is congruent to -1 times 4 times 10, which is congruent to -40. Now, there was a question before class started on how do you turn something from a negative number to a positive number? Well, you add some multiple of your modulus. So this is also congruent to -40 plus 17, or plus 17 times 2, or plus 17 times 3, and so on. So I'm going to start with plus 17 times 2. So that's 34. So this is congruent to -6. Or if you wanted the positive version, you add 17 again. And so this is also congruent to 11 mod 17. Now, one of the nice things about computing roots is that it's actually really easy to check if you have the right answer. So how would you check if you had the right answer? Well, you just take 11, you ask yourself, what's 11 to the 5th mod 17? And that should be equivalent to 10. And if it is, then that means you have the right answer. If it isn't, well, you did something wrong. In the exam, your answers can be both positive or negative. Yes. So I will allow you to put the smallest positive or the smallest negative number, whichever is more convenient. So like if the answer was -1, you could just put -1 instead of putting 16. Having said that, it has to be the smallest one. So if you put -18, I would consider that wrong. I mean, it's not strictly wrong, but it's not the simplest possible form. Okay, but of course, excuse me, listing out all different equivalent powers. So listing all these out, 1, 17, 33, 49, 65, well, that can take a while, especially if your modulus is quite big. And so you may want a faster way of doing that that doesn't involve listing out all the powers. Also, there's some chance that when you list out all the powers, it just won't work. So sometimes you won't be able to find a root, and you would be there sitting there listing out powers unto infinity. And so this isn't a strategy that is really that practical when you're dealing with a really large modulus. So instead, we can make use of the tools that we've been developing throughout the class to exactly compute it. Oh, can you explain how 10 to the 1 is congruent to 10 to the 17? Yes, I absolutely can. So note, 10 to the 16 is congruent to 1, right? So if 10 to the 16 is congruent to 1, well, what's 10 to the 1? Well, that is congruent. That is the same as 10 to the 1 times 1, right? So anything times 1 is just itself. But we know that 1 is the same as 10 to the 16. So this is congruent to 10 to the 1 times 10 to the 16, which is then 10 to the 17. Okay, so that is the cool part about Fermat's little theorem. Remember how when I was talking about labels in modular arithmetic, you have lots of different numbers with the same label. So like if you're in mod 11 arithmetic, the label 1 is the same as the label 12. It's the same as the label 23, and so on, right? So if you go around the clock, you have multiple labels for the same thing. It turns out that by using Fermat's little theorem, you get the same kind of effect for powers. So you can have lots of different powers that are the same thing. So 10 to the 16 is the same as 1. And so that means 10 to the 1 is the same as 10 to the 17. Not sure if this is relevant to this question exactly, but what is a unique answer like the one they asked for in the practice quiz? Oh, yeah. So one of the things that might happen is, let's see, what's an example here? Yes. So if I ask you, what's the square root of 1 mod 17? Well, it turns out that there are 2 answers to the square root of 1 mod 17. Well, at least. There actually might be more. I think there are more. But there are at least 2. There's 1. 1 is the square root of 1, right? But so is 16. Because 16 is just -1. And if you squared that, you just get 1 again. And so it turns out that often you end up with multiple answers. And often you end up with no answers. So there are many numbers where you don't have a square root in mod 17. And so when I ask for a unique answer, what I mean is there's only one answer. There's exactly one answer to this particular root problem. So like on the practice quiz, I'm basically saying, I only want the answer if there's only one answer. But now you might ask, well, how can I figure that out? If I just list these things out, I don't actually know if there are multiple answers. Well, that's why this particular method doesn't tell you if there are how many answers there are. And it doesn't even tell you if there are 0 answers unless you list them all out and then figure out that you're repeating yourself. But instead, we have another method that we were discussing on Wednesday that tells you both if the answer is unique and whether or not there always is an answer. So this is finding certain roots without listing stuff out. And this is a slightly more complicated algorithm, right? So there are multiple conditions now. So the first condition is, again, that P is prime. The second condition is A is not congruent to 0. And we have a third condition, which is that K, if we're dealing with a Kth root, is relatively prime to P minus 1. So if this is true, then there exists a unique solution to the root problem. If this is not true, you might have 0 answers or 2 answers or whatever. Okay, so we have our conditions. So then the trick is, we want to find 1 as a combination of K and P minus 1. And we're able to, and I've written this sort of this weird way, but in order to solve this, you can just make use of the same thing we've been doing for combinations all this time using the reverse Euclidean algorithm. Once you've done that, So I think last time I said that you immediately know that the answer is a to the n, right? But here I'm going to go through a little bit some more of the logic of why it's a to the n. Wait, come on. So notice that if 1 is equal to km minus L times p minus 1, well, that is taking, that is also saying that 1 plus, note that 1 plus L times p minus 1 is equal to km, right? By just adding on both sides. So this is also the same as saying 1 plus L times p minus 1 is equal to km. So that's basically what that's saying. And we also know that this is also equal because you can use Fermat's little theorem and add a multiple of p minus 1 to your power, and you get the same answer. Right? So what we're doing is we're just finding we're just jumping ahead. Instead of going a to the 1, a to the 1 plus p minus 1, a to the 1 plus 2 times p minus 1, a to the 1 plus 3 times p minus 1, and so on, you're just jumping ahead all the way to 1 plus L times p minus 1. And you're jumping ahead to the one which is a multiple of k. That's exactly what we're doing here with the reverse Euclidean algorithm. And then once we do that, well then taking the kth root of a is easy, because the kth root of a is the same as the kth root of a to the km, which is then just a to the m. And we know how to solve power problems. So let's give an example of this. So for example, if we had the 10th root of 5, so this is, notice this is the same one we did a moment ago. And so we're going to do it a slightly different way. So this is the 10th root of 5 mod 17. Well, so how we're going to do this? We're going to use the Euclidean algorithm, we're going to reverse it, and we're going to get a combination. So we know 16 is equal to 5 times 3 plus 1. 5 is equal to 5 times 1. And therefore, when reversing that, 1 is equal to 16 minus 5 times 3. Right? And if we're going to rewrite it in like this way, you can also rewrite this as 1 minus 16 is equal to minus 5 times 3, right? So what does that give you? Well, that gives you, if you're going to do it step by step, instead of jumping ahead. So if you, at this point, you could jump ahead and say a to the minus 3. But that's a little bit painful. So instead, what we're going to do is we're going to, instead of jumping ahead, we're going to do it step by step. And we're going to ask, well, that means that a to the 1, let me rewrite, is congruent to a to the 1 minus 16, right? Because of course, if you can add 16, you can also subtract 16. So it's congruent to a to the 1 minus 16, which is congruent to a to the minus 15. 1 minus 16 is minus 15. But importantly, minus 15 is divisible by 5, right? So that means that the 5th root of a is congruent to a to the minus 3. And now a to the minus 3 is, of course, congruent to a to the 13, because you can add 16 to it. So less. And notice that this is true for any a. We don't have, this isn't specific to 10. This is true for any a, but in particular, we know that the 5th root of 10 is congruent to 10 to the 13 mod 17. So same as on the previous slide. Importantly, you'll also notice that if I ask you for the 5th root of 9 mod 17, you could do it the exact same way, just 9 to the 13, because it doesn't actually depend on what you're taking the root of, assuming that it's co-prime to, sorry, that's relative, assuming that it's not equivalent to 0 mod p. Okay, so that was a quick review of the sort of stuff that we did, especially this root section that we did last Wednesday. Does anyone have any questions here? So I don't think roots are on your practice, or if they're not on your practice quiz. So they won't be on your quiz, but they will be on your next quiz. So, and I think powers are on your quiz. So they were on your practice quiz, I'm pretty sure. So make sure you know that. But let's try out a couple times using Fermat's little theorem to solve these problems. Of course, you don't always have to use Fermat's little theorem, but the question is, can you in these particular cases? And to find the answer. So let's start with an easy one. 3 to the 1000 mod 81. Someone's saying to wait and hold up. So whenever you get given a question, before you just run off and start doing the computation and following the steps, it is super important that you check if the algorithm is applicable at all. 81 is not a prime number. So it turns out that you can't use Fermat's little theorem. You still can compute this by using this by taking lots of powers and doing this sort of powers of 2, but it takes a lot longer. But so 81 is not prime. Not prime. So can't use Fermat's little theorem. Okay, good. So people have found that, but make sure you check these things, because the scary part about problems like this is you could do the entire algorithm. It would give you an answer. It would just give you the wrong answer. So make sure you check your conditions. Okay, what about 2 to the 666 mod 61? Sorry, there's a little net that's just floating around this podium. So of course, the first thing to ask is 61 prime? And for that, don't worry, I will give you the list of all the prime numbers smaller than 100 again. Oh, wait, I did not give you that on the quiz. That's a bit of an issue. I'll mention that to the TA, since I've already printed the quizzes, so yeah. Certainly on your final exam, there will be the list of primes. I guess I could just print out an extra handout with everything. Maybe I'll do that. Anyway, okay, so it looks like people figured it out. So let's work it through together. Well, 61 is prime, so that means you can use Fermat's little theorem. Fermat's little theorem states that 2 to the 60 mod 61 is congruent to 1, right? So that means that you can just take, so 2 to the 666, well, that's just congruent to 2 to the 6, right? Because 666 is 60 times 11. So, and this is congruent to 64, which is congruent to 3. So the answer is indeed B. Okay, let's keep on going. What about the cube root of 10 mod 57? I think those are some leftover answers. Let me zero those out. Good. It seems like people are paying attention. Is 57 prime? And the answer is no. 57 is not prime. So again, you can't use Fermat's little theorem. Oh, well, let me go back to the previous one since there was a question. 666 divided by 60. Well, that's 1. 60. 66. 1. 66. Remainder 6. Okay, but yes. So for this next one here, notice that 57 is not prime. Okay, great. So you guys are certainly double checking these things now. Make sure you pay attention to this. Okay, what about this one? The cube root of 10 mod 61. So now, as we discussed earlier, 61 is prime. Oh, was there a chat in the Zoom? Sorry, I'm not like actually watching Zoom chat. So if someone put a chat in there, I didn't see it. Okay, so it looks like we're starting to get some people converging on E again. Why E? Well, so strictly speaking, we're not. This isn't just using Fermat's little theorem, but the algorithm that we gave for finding roots doesn't work when you're dealing with 60 and 30, because 60 and 30 aren't relatively prime. So note that the GCD of 3 and 60 is equal to 3. And so the real answer, so I actually put down the wrong set of answers here. So the real answer is that you can't use the algorithm we gave. You technically can still use Fermat's little theorem, but you can't actually use the sort of division algorithm that we gave last time. Let's see. So you'll notice that some people answered B for 3. So now, if you had answered B, one of the things that you should do is you should check your answer. So the question is 3 a cube root of 10? Well, what is 3 cubed? 3 cubed is congruent to 27 mod 61, which is not congruent to 10. And so if you had somehow gotten the answer 3, that would have been wrong, and you would have known that it was wrong if you just plugged it back in. Okay, one last one. What about the cube root of 10 mod 11? So hopefully by now you recognize that 11 is prime. So for anyone who is writing down an answer, I strongly suggest that you plug it back in and see if your answer is right. So it looks like some of you have gotten the answer 5. Plug it back in. What is 5 cubed? And I'll give you a hint, 5 cubed is 125. And so you should check to see what that is mod 11 and see if that answer is actually 10. So let's take a look. 125 divided by 11. Well, that's a 1, 11, 15, 1, 11, 4, remainder 4. And so the answer is not actually 5. Okay, but we're getting a decent number of answers. So let's go, let's go ahead and solve this one. So there are a couple different ways you can approach this. One is you can use the recurrence Euclidean algorithm and all that, but it turns out that for this particular case, since I don't have that much space, I'm just going to do it the sort of intuitive way. So I'm going to, the first thing you should ask is the greatest common divisor of 3 and 10 equal to 1? So are they relatively prime? Yes, 3 and 10 are relatively prime. And then the other thing you might notice is that the cube root of 10 is congruent to the cube root of 10 to the 11, because Fermat's little theorem says 10 to the 10 is congruent to 1 mod 11, right? Which is congruent to the cube root of 10 to the 21, right? Okay, but 21 is divisible by 3, so this is congruent to 10 to the 7th. Okay, and what do we have? So we have 10 squared is congruent to 100, and what's 100 mod 11? 100 mod 11 is actually quite easy. 100 mod 11 is just congruent to 1. Right? Another way of seeing this is that, of course, 10 is just minus 1 in mod 11. And so minus 1 squared is going to be 1. And so then 10 to the 4 is also congruent to 1. And so then 10 to the 7 is congruent to 10 to the 4 times 10 to the 10 squared times 10, that's 6 times 10 to the 1, which is congruent to 10. And so the answer here is actually D. Okay, any questions about that? So this is quite complicated. There are several ways of doing it. So in this particular case, I did the sort of intuitive way as opposed to doing it the sort of formal way that we gave the algorithm for in the last slide. But there are a number of different ways of finding these roots, and you should start slowly getting comfortable with them. So now, one of the things that you all might have noticed is that I gave you a lot of trick questions on this slide. So there are a lot of questions. Oh, can you explain the first 2 steps you did in the last one? Oh, yeah, so let me explain that again. So here, the key is 10 to the 10 is congruent to 1, right? So that's Fermat's little theorem. 10 to the 10 is congruent to 1, and therefore 10 to the 1 is congruent to 10 to the 1 plus 10, which is just 10 to 11, which is congruent to 10 to the 21. And so I was able to plug those things in. The whole point of Fermat's little theorem is it gives you a bunch of different labels for the same thing. And of course, there are more sophisticated ways of sort of jumping ahead in labels, but one naive thing you can do is you can just look at the next couple labels. Okay, but anyway, so I gave you a lot of trick questions on this one. It seems like quite a few, whereas in the past, like usually like the algorithm I gave you would work for the problems that you're dealing with, right? But that hasn't been the case. And that's one of the things that mathematicians care about a lot, is really thinking about when things work. When does a particular algorithm work? So Fermat's little theorem and the methods related to it only work under certain conditions. When they work, things are a lot easier, but they don't always work. So then the central question for a mathematician is, well, A, figuring out when they work, but then B, you might ask yourself, what else can you do in similar circumstances where it doesn't quite work? So there are some questions. Why do we need the modulus to be primed? So this is a very important condition for Fermat's little theorem. If you don't have it, then things just completely break. Then another question might be, well, what if the modulus isn't prime? Can you still get something that's sort of like the Fermat's little theorem? Can you still do something similar? Because Fermat's little theorem makes things a lot easier. Is there anything analogous when you don't have prime modulus? So, well, let's think about it. What are some of the ways that we figured out patterns, things to prove? So we've been having a lot of sort of hands-on activities over the last couple of weeks. So what are some of the ways we've been trying to figure out these patterns for things to prove? Answer in chat, or you can just shout them out. So like, what have we been doing? What have we been doing as mathematicians? Yes, we tossed balls in circles. We experimented on multiplication tables. That was what tossing the balls in circles was. That was literally you coming up with multiplication tables in the physical world. Yes, exactly, tables. So then we also had the power tables and things like that. So look, yeah, so the other thing is we've been looking at proofs, find the remainder. Yeah, so we've been doing all these different techniques for trying to figure stuff out. Well, yeah, noticing repetition. So we did a lot of experiments. We wrote them in the tables. It doesn't have to be tables. We wrote them all down, and you're like, well, what's going on here? You try to notice things that happens, and then once you've noticed them, you're like, well, maybe this is a general trend. And another thing you can do is you can make guesses based on analogies to other similar things. So for example, roots are harder because it's reversing something. And we already know that subtraction and division, which are reversing operations, are harder than their analogous forward operations. And so you can make these sort of general guesses as well based on analogies to other things you've done. But the sort of key is that we had all these different methods. Today, we're going to, and on Wednesday, we're going to spend some time and really dig into another approach, which is one of the other ways that mathematicians really approach these things, which we haven't covered as much because it is in some ways a little bit harder. It's certainly a little bit different. But another way that mathematicians figure these things out is just by carefully studying proof steps. So like operating in the realm of pure logic and trying to figure things out just by thinking about them without having to necessarily do a lot of experiments to sort of point you in which direction to think. So, as a reminder, how did we come up with the Fermat's little theorem? Well, we wrote out these tables, and you noticed that a to the 6 and a to the 12 and a to the 0 had entire columns of all ones, right? So that's how we came up with Fermat's little theorem. The sort of idea for it is like, well, here we're in mod 7, and in mod 7, it seems like multiples of 6 are always all one columns, right? And so to get the conjecture here, which we proved, the conjecture is that a to the 6 n is congruent to 1 for any n, right? So that's a conjecture, and you can sort of you showed this, and you can prove this a couple different ways. One way for proving this specifically for mod 7 is you can just be like, well, you can just see that everything repeated. Things constantly repeat, and so every 6 things completely repeat, and so therefore you do know that every 6 powers you end up getting an all ones column. And sort of a higher level conjecture. So another conjecture is that a to the p minus 1 is congruent to 1 for any mod p for any p, any prime p. So you have these different levels of conjectures. So the first level might be you're conjecturing something specific about one particular number system. And then you might have a more general conjecture, so which leads to a more general theorem. Oh, well, maybe this works for any prime p. And then once you get to that step, one thing that you might do is you might be like, well, I'm going to conjecture that works for any number. And that conjecture would be wrong. And you can you figure out that's wrong by showing certain counterexamples, but like that's sort of the direction, right? So you start with these specific examples and you try to generalize. So you try to tell yourself something about something bigger. So you don't just want to deal with mod 7, you want to deal with mod p for any prime. And now the sort of thing that we eventually want to do is we want to find out, well, we already know that it doesn't work for any number. But the question is, can you come up with a more general theorem that does work for any number, and then still also works for the primes? It clearly won't be the same theorem, but it would be a theorem that would encapsulate it. And that's what we're going to get to on Wednesday. We're not going to have enough time today. Question, would a to the 18 be also 1? Yes, it would. And that is exactly the sort of conjecture. You see this pattern and you're like, well, it repeats every 6. And so then maybe a to the 18 would also be 1. Now, as a mathematician, you might even conjecture for any multiple of 6, which is exactly this conjecture here. And then if you're like really, really clever, you might be like, well, maybe it's p minus 1 for any prime. Okay. So in order to really carefully understand that, we're going to have to really dig into the proof of how we prove Fermat's little theorem. So I'm going to remind you, I threw up this slide back about a week ago. Actually, I think exactly a week ago. And we sort of went through it really fast. And it seemed like a lot of people didn't really fully understand what was going on. But now we need to dig into this because we need to really understand what's going on here in order to understand why Fermat's little theorem works in certain cases and doesn't work in other cases. So each of these steps, I'm going to go through them slowly, not in this order, because this order was an order of sort of talking about intuition based on the beanbag experiment. Now, what we're going to do is we're going to talk about it in the sort of order that you would want to write it out in a proof. So step 0, you're going to list your start and end. So one of the things that we know we need is that p needs to be prime. So for example, if p is equal to 4, then our proof won't work. Right, so that's one of the starting conditions. We also have another starting condition, which is that a is not congruent to 0 mod p. So that is, if a is equal to 0, or a is equal to p, or a is equal to 2p, etc., then our proof won't work. In fact, not only will our proof won't work, the theorem won't be right, because you can't have a 0 to some power be equal to 1. Like that just doesn't work in the prime modulus. And then so those are our starting points. And then we also have our end point. which is our claim. So what we're trying to prove, a to the p minus 1 is congruent to 1 mod p. So this, of course, is our goal, given those conditions. So that's what we're trying to prove. And when you're doing this, what you're trying to prove is that both sides, this side here and this side here, are actually equivalent. And often when you're trying to prove these equivalences, one thing you might do is you might try rewriting one side or the other until you get the same thing, right? So like if I have a linear equation, which we started with at the very beginning of class, well, what you do is you do the same thing to both sides until you get it in some nicer form, right? So maybe you divide both sides by 2, or you subtract both sides by x. And so we're going to do the same kind of thing. We're going to rewrite these sides. So, well, the right side 1 is not so interesting to rewrite. We're going to rewrite the left side, a to the p minus 1, in such a way that we can show that it actually is equivalent to 1. So, well, let's start. Because p is prime, we can divide by all numbers except 0. Right? So this is one of the nice things about working in a prime modulus is you can do division. You can't divide by 0 still, but you can divide by anything else. And, well, we know that a divided by 1 is just a, right? Well, then that's also equal to 2a divided by 2, right? That's also a. And that's the same as 3a divided by 3, and so on, all the way to p minus 1 divided by a over p minus 1. So why can I not write this? Why is that wrong? Exactly, it would be undefined. So this is wrong because p is congruent to 0, and you can't divide by 0. But you have all these other things that you can divide by. And so these are all different ways of writing out a. So what we have is now we have p minus 1 ways of writing a. And this is where the p minus 1 in our theorem comes from, somehow. It's because you can do p minus 1 different ways of dividing, but you can't do p different ways of dividing because you can't divide by 0. Okay, well, once you've done that, well, then we're going to, when we say p minus 1, what does that mean? Oh, that means, well, when you're in mod p, you have p different numbers, right? 0, 1, 2, 3, 4, 5, all the way through p minus 1. So when we say p minus 1, that means if you're in mod 7, p minus 1 is 6. If you're in mod 13, p minus 1 is 12. Because p is the modulus. Okay, well then once we've done that, then a to the p minus 1, well, that's a power, right? So that means we can rewrite this as a times a times a times a. How many times? P minus 1 times. Right? That's just the definition of a power. But now what we're going to do, the clever thing about this proof, and this is highly non-trivial to come up with, so don't worry, like, coming up with this idea is brilliant. We're just trying to understand it. So what we're going to do is for the very first of the a's, we're going to replace it with a over 1. For the second a, we're going to replace it with 2a over 2, and so on. So this is congruent to a over 1 times 2a over 2 times 3a over 3, and so on, all the way to p minus 1 a over p minus 1. Okay, so we're just doing our substitution. So that's all still fine. Okay, so that's a sort of weird way of writing out a to the p minus 1. And now we're going to try to understand that. Well, step 2. Notice that multiples are all numbers. By which I mean that the set of all multiples is the set of all numbers. And so this came from the beanbag tossing experiment, where you show this empirically, but you can also prove this. So notice, if the greatest common divisor of a and p is equal to 1, then A, 2A, 3A, 4A, and so on is all numbers in P. In mod P. In mod P, because we can write a combo 1 is equal to Ka plus Lp, right? So if the greatest common divisor is 1, then you can write a combination, which then implies that 1 is congruent to Ka, right? Of mod P. Right, so you're just taking mod P of both sides. But then you also know that 2 is congruent to 2 Ka, 3 is congruent to 3 Ka, and so on, all the way to P minus 1 is congruent to P minus 1 times Ka, and P is congruent to Pka, and this is all mod P, of course. Okay, so every single number you can write out as a combination, and therefore the multiples will get you to all the different numbers. This is the reason why when you toss the beanbags around, you did end up getting to everyone if the two numbers are relatively prime. Okay, and we're almost there, and I'm almost out of time. So let's see if I can finish this off. So now the next question is what is the sort of pattern you get? And one of the things you might have noticed when you were doing the beanbag tossing is if they got to everyone, then they got to everyone before you repeat it. So the sort of mathematical way of writing this is multiples go through all the non-zeros in a cycle before returning to 1. And so you know this, 0A, 2A, all the way to P minus 1A, PA, and you can keep on going, which would give you P plus 1A, and so on. We know that that's all multiples of A. And furthermore, we know that PA is congruent to 0 mod P, and P plus 1A is congruent to A mod P, right? And so on. So the cycle repeats. So the cycle repeats after P steps. But we can get all P numbers in mod P. So each cycle must contain all numbers, contain all of them. Okay? So thus, we know that the set of multiples in a single cycle, which is all the way up to P minus 1A, we know that this happens to be all the different numbers, right? But we also know that each of these is exactly length P, and so if we could take out 0 out of both of them, we also know that, so these are as sets of numbers, as sets. So they might be a different order. But we also know then that if we take out the zeros, A, 2A through P minus 1A, this set is the same as the set 1 through P minus 1. So you've taken out 0 from both sets. And now we're basically there. So let me just finish this off. Putting it all together from step 1, A to the P minus 1 is congruent to A over 1 times 2A over 2 times 3A over 3 times all the way through P minus 1, A over P minus 1 from step 1. And you know that the top set and the bottom set are the same sets of numbers. So then that's all congruent to 1 mod P, because the top and bottom are the same sets of numbers, and so they cancel out. And that finishes the proof. So there are several different steps, and in each step you had to think about why things were the way they were. And now if you go back and examine the proofs, step 1 depends on the prime P in order to divide, right? That's the reason we could divide. So maybe in other circumstances, we can find other circumstances when we can divide. Remember, like when you have a prime, you can always divide. But with other numbers, you can still sometimes divide. Step 2 uses A not congruent to 0 mod P to see that the greatest common divisor is equal to 1, which makes the multiples possible. And step 4 then use the number of non-zero numbers in mod P, which is P minus 1. So those are all numbers you could divide by. And so then the cycle length with A to the P minus 1 is congruent to 1. Maybe when we're not working in the prime, we can still find some other shorter cycle because you have some fewer numbers that you can divide by to do the same sort of canceling out. And maybe we can find something that still works. And so next time, we're going to prove what's called Euler's theorem. I mean, Euler had a ton of theorems, but this is one of his theorems, which generalizes Fermat's little theorem to non-prime modulus. And so that will be what we're going to do on Wednesday. I am out of time, so thank you all very much. Reminder that their quiz is this week. Please show up. And I will see you all on Wednesday. Bye, everyone.